So, as a British lad, there are a few things more nostalgic to me than a 60s sci-fi show that featured a madman with a box, some of the very best and very worst of TV sci-fi, and memorable monsters such as this random assortment of licorice all sorts called the Candyman. Hello everybody and welcome back to another episode of The Science Of, the show where I take a look at the science behind your favourite game shows and more. Today, we're taking a look at the UK's biggest cultural export outside of Queen-themed tea towels. Doctor Who, the show where a never-ending list of actors and actresses play the titular Gallifreyan as they travel through space and time righting wrongs, defeating all shapes of alien threat. The show has been running since 1963 with the first Doctor, William Hartnell, and since then it's evolved and developed into a staple of British sci-fi. Once Hartnell was too old for the role, Regeneration was introduced into the show. This allowed Hartnell to give the role to Patrick Troughton, and this provided the show with almost unmatched longevity. Whilst the visuals of transformation have changed over the years, whenever the Doctor has been close to death, they've always been able to regenerate into a new body and form a new personality, normally in response to whatever came before. The second Doctor's run introduced another key element of the series, the sonic screwdriver that's grown and evolved over the series.
This is a sonic screwdriver. Now, where can I demonstrate? That revolver will do. There we are.
To the point that the little glowy lit up model carried by the 9th Doctor onwards is almost unrecognisable from the simple pen-like device carried by Troughton. The 3rd Doctor, John Pertwee, featured a version of the Doctor stuck on Earth after the event of Troughton's last episode. And in his first episode, Pertwee's Who introduced another factor that's been kept as canon throughout the series, with Spearhead from Space being the first episode to establish that all Time Lords have 2 hearts. So what we're going to do today is take a look at Gallifreyan biology to see how their circulatory systems and regeneration correspond to real-world organisms. So let's start out by looking at the Doctor's 2 hearts. Whilst it's never been outright said whether these look like human hearts or something different, they've been shown to us in multiple episodes in New Who, with the best look at the binary vascular system appearing in the episode The Power of Three, where a scan taken by Kate Stewart shows us both of the Doctor's hearts side by side, and they look like 2 human-sized hearts. Just like the human heart, I imagine these 2 Gallifreyan hearts carry both oxygenated and deoxygenated blood around the body, and that's why the Doctor is able to survive a strike to one of his hearts without dying. The human heart is split into 2 sections, one that pumps deoxygenated blood to the lungs, and another that pumps oxygenated blood from the lungs around the body. It's able to do this thanks to a set of 2 atriums and ventricles separated by a muscular wall called the intraventricular septum. Between these chambers there are atrioventricular valves which allow the blood to move between the atriums to the ventricles but not back up the other way. From the ventricles the blood either goes to the left pulmonary artery to the lungs or from the left ventricle to the aorta, where it's pumped to every cell in the body. The sequence of events that causes the heart to pump is based around a depolarization of smooth muscle cells' plasma membranes. The gap junction that connects these cells allows action potential to spread from one cell to the other, triggering a chain reaction, exciting all of the cardiac cells. The initial depolarization arises from a small group of conducting system cells called the sinoatrial node. The sinoatrial node is the pacemaker for the entire heart. Its depolarization generates the action potential that leads to the depolarization of all other muscle cells and determines a person's heart rate, the number of times the heart beats per minute. The wave of depolarization first reaches the muscle cells of the atria, causing them to contract around the same time. From here, the depolarization wave then hits the atrioventricular node, which carries the energy down a bundle of fibers called the bundle of His. And these then divide into left and right bundle branches which enter the walls of both ventricles, joining with Purkinje fibers which conduct and spread the impulse throughout the rest of the ventricles. These fibers ensure a single coordinated contraction that starts from the bottom of the ventricles and moves up rapidly. This is what causes blood to be pumped around the body. But is it possible for a person to have 2 hearts? And what could the possible advantages be? Well, it might be surprising to you, but we've actually been able to do this since all the way back in 1974. For those of you who only understand times in terms of Doctor Who, this is around the time of Tom Baker. Heterotopic heart transplantation is a surgical procedure that allows a second heart to be connected to the human heart in a parallel fashion. This causes the new heart to assist the patient's native heart and maintain circulation in case of a rejection episode. Now this isn't exactly the same as a binary vascular system, as the new heart is normally something like a pig's heart rather than two human hearts, but it's the closest we have to compare to the Doctor. There are some members of the animal kingdom that have multiple hearts however. The octopus for instance has 3 hearts, one that pumps blood throughout the rest of its body and 2 additional ones that pump blood over gills. But that's enough about the vascular systems of Timelords and octopi. What about the Doctor's regenerations? In the show, the Doctor has been shown to be able to change every cell in their body upon dying, changing everything about their physicality and personality. Whilst this ancient magic of the Timelords is incredibly unrealistic on the surface, it actually occurs in every multicellular organism on a daily occurrence. In biology, regeneration is the ability to recreate lost or damaged tissue and organs, re-establishing their natural morphology and function. This can be exemplified by wound healing mechanisms, which I showed off in my video on the science behind Star Wars Bacta Tank, where I illustrated how the epidermis is re-established after the skin gets cut or burnt. But this isn't necessarily the same kind of regeneration as illustrated in the show. A few cells replicating isn't the same as regrowing limbs. In the 10th Doctor, David Tennant's first episode The Christmas Invasion, the Doctor is shown as being able to regenerate single limbs after having his hand cut off in a sword fight with a Sycorax, owing to an abundance of regeneration energy. Whilst the cause behind this are as scientific as the moon being a giant egg, there are many organisms that have the ability to regenerate missing body parts. Deer can regrow their horns if they're broken off by fighting with other deer, but this is thanks to their diet, which is packed with calcium and phosphorus. However, I can understand if this isn't impressive to you, as horns are less complex tissue than something like an arm. So what creatures can regrow entire limbs? Limb regeneration is a complex yet fascinating process that is seen in its entirety in Eurodole amphibians. This is accomplished by the formation of a morphologically uniform intermediate, a blastema. This process takes place in a few stages. It starts with wound healing. Immediately after amputation, the damaged tissues of the limb are characterized by erythema and edema, which are consistent with the initial phase of wound healing response to injury that I've outlined previously. It involves the degradation of nerves at the wound site and an inflammation response, which is followed by the migration of keratinocytes over the amputation site in the formation of an apical epidermal cap, which serves a key role in facilitating regeneration. Once wound healing is complete, after a week of amputation, blastema cells begin to aggregate under the apical epidermal cap. The largest contributors to blastema formation are dermal fibroblasts. These can be seen migrating from the dermis of the wounded stump towards the centre of the blastema between 5 and 10 days after amputation. These cells make up about 43% of blastema cells and are highly beneficial owing to their ability to de- and redifferentiate. In experiments using the axolotl accessory limb model, it was found that these dermal fibroblasts de-differentiated to regenerate cartilage in addition to connective tissue fibroblasts. The method used to regenerate bone is somewhat less well known, and is still being heavily investigated, with the axolotl model illustrating that, even without any skeletal remnants, skeletal tissue can still be regenerated. This has been theorized to be thanks to subpopulations of de-differentiated dermal fibroblasts, showing just how important they can be to this regeneration process. Now we come to the last stage of regeneration, the formation of new musculature. Muscles are actually one part of the body that mammals, reptiles and amphibians can all regenerate quite easily. This is due to the presence of muscle satellite cells. Skeletal muscle has the capacity for growth and repair throughout an animal's lifetime. This is one of the key components of muscle growth in general. This normally quiescent group of cells is characterized by the expression of paired box 7, a transcriptional factor otherwise known as PAX7, that not only defines the population, but is also necessary for satellite cell mediated muscle growth in response to injury. These satellite cells both self-renew and give rise to myoblasts, differentiated daughter cells. All of these wouldn't be possible without blastema formation, with these de-differentiated cells producing dermal, skeletal, skin, nerve and muscle tissues. The reason that humans can't regenerate limbs is that we are unable to produce adult stem cells that can de-differentiate in the same way that amphibians can. Humans can only replace a superficial layer of skin, in the process previously described as homeostasis. Adult humans do have sufficient stem cells to allow regeneration of blood vessels and even nerves, but they don't seem to be active to the point of generating all other things needed for growth on a large scale. So there we go. Out of all of the aliens seen throughout Doctor Who, the Gallifreyans are far from the least realistic. Whilst their regeneration is incredibly inaccurate, their binary vascular systems is within the realm of probability for humanoid organisms. Later down the line, I'd love to take a look at some of the other aspects of the show, focusing more on the technology behind the Timelords, specifically the TARDIS, its chameleon circuit, and the Doctor's sonic screwdriver, to investigate their basis in scientific facts. Then there are the numerous monsters and aliens seen throughout the series. I'd love to cover the science behind the clockwork robots that crew the SS Madame de Pompadour. Either way, I'll definitely be returning to the series time and time again. As always, if you enjoyed this video, then don't forget to leave a like, comment and subscribe to the channel. And if you want to help combat the ever-changing and frustrating YouTube algorithm, then make sure you share the video to help my channel grow. If you have any scientific subjects or topics that you'd like to see me cover in the future, then please tell me in the comments down below. As well as that, follow me on Twitter to get updates on the latest science of videos, and join my Discord for chats about science, gaming and more. But until next time, this has been the Science of Doctor Who. I'll see you next time. Thanks for watching. If you're looking for game-based content, then you can join me over on Twitch, where I live stream 3 times a week playing all manner of games suggested by the community. Or if you want to support the channel even further, then you could also contribute to my Patreon, where you'll get behind the scenes access to the creation of all videos, as well as being able to vote on what the next Science of video will be.